So, in the previous problem, the base was 3. We have a specific base called the natural base, which is denoted by the letter e. So, the function y equals e raised x, or f of x is equal to e raised x, is the natural base exponential function. And what is the value of e? The value of e is 2.71828. And you can see that the graph of e raised x, it looks like any other exponential function. For example, we could look at y equals 3 raised x over here, and y equals 2 raised x over there. So every exponential function, pretty much they look the same. The only difference here when we use e is that we call it the natural base. Different calculators have different options when it comes to exponential functions. So depending on the calculator that you intend to use, you can easily find a button that says E in the calculator, and all we have to do is plug in the value for x and we will get the value of an exponential. So here we are trying to evaluate e raised 3.4, and that would be 29.9641. So if you can't do it that way, you could also do 2.71828 raised 3.4. It should give you the exact same answer, or something very close. Plug it in the calculator again. And lastly, this is an exponential function, but we have 5 raised to the power of root 3, which is 5 raised 1.732. You can use, typically in a calculator, this is x raised y. So most calculators would have the button as x raised y. For instance, that right there has x raised something. So in our case, x would be 5, and that square up there would be square root of 3. So if I plug this in the calculator, I get 16.2425. So we all have credit cards, and they have variable rates, and typically interest when it is applied in credit cards, the interest rate is compound interest. And the simplest formula for compound interest is P times 1 plus R divided by N raised to the power N times T. Where P is the initial amount of the loan and N is the number of times we apply the rate, because we are compounding the interest, and T is the time for which you have this particular loan or investment, or anything that involves compound interest. Here, the key thing to notice is that N is the number of times we apply compounding. But if we have to apply interest in a continuous fashion, in other words, we don't have a fixed number of times when we apply the interest, rather than continuously throughout the year we choose to apply the interest, then the formula reduces to P times e raised RT. But just think of the deodorant, but So this case is when we apply the interest continuously. And E is our usual natural base. And that approximate value is 828, 2.71828. So here is an example where you have $6,000 to invest. Which investment yields the greater return over 4 years? 8.25% compounded quarterly, 8.3% compounded semi-annually, and 8.2% compounded continuously. So the principal amount here is 6,000, and the rate is 8.25% for the first case. It is quarterly, so we are going to apply the interest 4 times per year. And the time is 4 years. So using the formula, we simply plug in 4,000 times 1 plus. Do not forget to convert the percent to a number. Oh, that's a bad choice there. So it would become 0.825 divided by 4 times per year, so n is 4, and 4 times 4, we get 16. So you can use a calculator to evaluate this. And the amount is 5,545.226. So the first case, the interest accrued would be that amount minus the principal. So 5,545.226 minus 4,000. You end up getting 1,545.226. The second case, the rate is 8.3% compounded semi-annually. So the principal doesn't change, it's 4,000. The term doesn't change, it's 4. But number of times is 2 because we apply the rate 2 times per year, semi-annual. And the rate here is 8.3%, so that would be 0.083. So we use the formula. A is equal to the principal times 1 plus r over n raised nt. So 4,000, 1 plus 0.083 divided by 2 raised 2 times 4. So we would end up getting that, and you can use a calculator as always. And we end up getting 5,537.761. So the interest accrued would be this final amount minus the principal, which should be $1,537.76. The last case is 8.2% compounded continuously. So this would imply the formula is A equals P times E raised to RT. P is 4,000. The rate is 8.2% now. So the third case is 8.2%. The time is still 4 years. Since we are compounding continuously, we have the formula per. So 4,000 times E raised 0.082, converting percent to a decimal, times 4, which should be 4,000 E raised and use a calculator. And we get the amount as 5,552.76. I'm sorry, 5,552. So the interest accrued in this case is the amount, the final amount at the end of 4 years minus $4,000. We get 1,552.76. So the three cases, 8.25%, 8.3%, 8.2%. The term is fixed, the principal is fixed. N initially was 4 times, that would mean quarterly. 2 times, semi-annually. And the last one is continuously. And the accrued interest case 1 was 1545.23. Case 2, 1537.76. Last case, 1552.76. So obviously, continuous compounding is the way to go. Even though the rate is small compared to the other 2 cases, we get a better yield at the end here because of the fact we are compounding continuously. Unfortunately, most investments do not compound continuously. So here we are going to do a few more problems on exponents, specifically natural exponents. Here we have the demand function for a product, and it is modeled by the expression that is given in the question. And what we have here is an initial amount, which in this case is 10,000. So if we understand the behavior of this particular function, we would know what happens over time. So the price is given by p, and it is a function of x. And p of x is equal to so we want to evaluate the price with respect to x. The first is when x is 1,000, the other is when x is 1,500. So the two values are 1,000 and 1,500, and we want to find p of x. This is very straightforward, especially if we had a calculator. So I'm going to put in the function first. Parentheses are important. E raised negative 0.001x, close paren for the exponential, close paren for the denominator, close paren for that rational function, and finally 1 for the open parentheses. And when we graph it, we are going to get a good idea about the function. So as of now, we're not able to see anything because there are things wrong with the window. But I'm going to table set and evaluate values of the price for x is equal to 1,000 and x is equal to 1,500. So second window, I'd simply say the independent variable x to be asked, and that's all the setting that we have to do. And now press second graph to get a table. So when we plug in 1,000, we end up getting 1,092.3, and when we plug in 1,500, we get 692.28. So if you look at the expression, x is the number of units in demand, and p is the price. So as the demand increases, we can set an appropriate price. For example, the more we have in demand, let's say instead of 1,500 we had 3,000, the price is going to decrease because we have more in demand. So if I keep on changing the value of x from 1,000 to 1,500 to 3,000 and all the way up to, say, 10,000, eventually this is going to become 0. So it is becoming 0.15133. So if there is a demand for 10,000 units, then I can set a price as low as possible to make profit. And that's what we're going to address with part C. What is the limit of the price as x increases without bound? Obviously, as this approaches infinity, that value is going to become 0. There is an easier way to do this without the use of a calculator. So if I take the limit x approaches infinity, p of x, that would be 10,000. The limit doesn't affect 1, so we'll move the limit to the term inside. So when we apply the limit, the numerator would remain as is, the denominator 3 plus, e-raised, the x is approaching infinity, so we would end up having e-raised negative infinity, which is a rapid decay towards 0. So we would end up having 10,000 times 1 minus 3 over 3, which is 0. And that's the conclusion that we had over here. And let's graph it to see if it in fact goes to 0. So we have to choose appropriate ranges in this problem. So let's say the minimum value is 0 and the maximum value of x is 10,000. Or maybe we'll do 100,000. And let's go a scale in steps of 5,000, which is a lot. The y value, we would start at the initial value of, a maximum value of 15,000 because our initial value is 10,000, and a minimum value would simply be 0. And if we graph, I have to adjust the scale here, so I'll adjust the scale by 1,000 and we'll graph this. Hopefully we'd see it. We could actually see a curve. I see a tiny curve. Perhaps I'll change the scale and have it that way, and you can see it's going towards 0. Adjust the y value also. And there is our curve if it goes in steps of 3,000. Trying to get to an appropriate window. And you can see the curve, and it is approaching 0 rapidly as we change the value of x, which is the number of units demanded. So you can either use the limit to find the limiting value, or you can use the calculator to determine the limiting value. So here is another problem on exponentials. The population of Zambia from 1950 through 2013 can be modeled by that expression, which is p equal to 2.49 e raised 0.0276 t. And t is the time in years, and t equals 0 would simply mean the year 1950. The expression p, I could also write it as p of t. So if time t is equal to 0, we would have p of 0, that is 2.49 e raised 0.0276 multiplied by 0. Any number raised to the power of 0 is 1, so we have 2.49. So the initial population t equals 0 would be the year 1950, and we would have 2.49 million. So now we want to tabulate the values for each year that is specified. So the year would be 1950, 1960, 1980, 1990, 2010, and 2013. So the corresponding t values would be 0, 10, 20, 0, 10, 30, 40, 60, and 63. So how do we find the values? The population is in million, and we already know the first value is 2.49. To find the rest, we don't have to type each one into the calculator. We could make use of the table set function and the table function in the TI-84 calculator to get the answer. So let's go y equals, put in the function, that would be 2.49. Exponential 0.0276x, and enter, quit, go to table set, and we have a setting for start value of 0, which is what we have, and the independent variable is t. The calculator is going to ask us for the value of the independent variable, so our settings are just fine. Second mode to quit, second graph to get to a table. I'm going to delete all of those values. When I plug in 0, we get 2.49 as expected. When I plug in 10, I get 3.28. When I plug in 30, 5.699. When I plug in 40, I get 7.51, 60, 13.04, 63, 14.17. The year 2023, which is in part C, would correspond to 73. And plug in 73, we get 18.673. So the population in the year 2023 would be 18.673 million. And to answer part B, which asks why the change in population from 1950 to 60 is not the same as the change in the population from 1980 to 1990. Clearly it is not the same. The reason being the growth here is exponential. Not linear. If the change is linear, then we would expect a constant slope, but that isn't the case. Here we have an exponential growth. In other words, whatever amount of increase that we had between the year 1950 and 1960 will not be the same, and things are going toward infinity rapidly. So in a matter of 73 years, the population increased by approximately 16 million. So the reason why the change in population from 1950 to 1960 is not the same as the change in population from 1980 to 1990 is because the growth is exponential and not linear. Here is another example that uses exponentials, natural exponents. So in a typing class, the average number of words per minute typed after t weeks of lessons can be modeled by the expression n of t equals 95 divided by 1 plus 8.5 e raised minus 0.12 t. So we would like to know as to what would happen over time the average number of words that we would type after 10 weeks and after 20 weeks of lessons. So even before we start the problem, what we can do is take the limit as t approaches infinity, which would mean 95 divided by 1 plus 8.5 limit t approaches infinity e raised minus 0.12t. The reason being that is the only term that has t in it. So when we apply the limit e raised minus 0.12 and t is approaching infinity, this term rapidly decays to 0. So what would happen is we would end up having 95 over 1 plus 0, which is 95. So this simply means the more time we spend learning how to type, the more we can retain. The number of words that we could type would increase, the average number of words that we could type. But the limiting value is 95. We would always maintain an average number of 95 words per minute. So no matter how much time you spend learning how to type, the maximum number of words that you can learn to type on average is 95. Now, would that make sense in our case? So let's go ahead and graph it first before we proceed. So what we have is 95 divided by 1 plus 8.5 exponential negative 0.12x instead of t, and graph. Well, we have to adjust the window. So 0 maximum, we'll call it 100. And we will increase in steps of 5 or 10. Y max, we'll call it 100, and we will increase it in steps of 20. And let's graph this. And you can see things plateau over time, and no matter how much time you spend, time is on the x-axis, we're going to plateau at a certain number of words, and in this case, that would be 95. So the maximum average number of words that you are going to learn, no matter how much time you spend, is 95 words. That being said, how do we find the average number of words per minute typed after 10 weeks of learning, after 20 weeks of learning? All we have to do is plug in 10 and so we already have 10. For 10, the value of the function happens to be 26.684. So approximately 27 words. And let's just plug in 20 here. And if we spend 20 weeks, we would have 53.6, so approximately 54 words. If we spend 30, we would have 77 words. But you can see beyond a certain point, no matter what I plug in, no matter what time I spend, in that case it is 73 weeks, we have about 94.875 words, that is 95 words. Even if we spend 200 weeks, we'll have 95. 2,000 weeks, still 95 words. So we have a limiting value of 95 words. So that is a inhibited growth model, in the sense eventually the growth plateaus and it is inhibited, and it is inhibited at a maximum value of 95. So here's another exponential problem, and just in the previous problem we had e raised negative 0.12 times t. Even though we see a negative there, this is not a decay problem. The reason being that exponential is in the denominator. If we move it to the numerator, the exponent of e would become positive. So the previous problem is a growth problem. Specifically, inhibited growth. Here, it is going to be a decay problem, and it will decay to 0. So even before we start the problem, let's take the limit of P of t. What is P of t? P of t is the average time between incoming calls at a switchboard, and that time is 3 minutes. If a call has just come in, then the probability that the next call will come within the next t minutes is given by that probability. So time t, we have the probability as 1 minus e minus t over 3. And the average time between calls is 3 minutes. So we want to find the probability of the following situations. The first one, what is the probability that we would get a call in the next 5 minutes? And that would simply be so let's go ahead and put in the function 1 minus e raised negative t over 3. Table 5, I get 81% chance. And in the next 6 minutes, now you have to think about this logically, even before we use calculus. The probability of time between calls is 3 minutes, and I'd like to know what are the chances that I would get a call in the next 6 minutes. In other words, there are 2 3-minute intervals, and we know on average we get a call every 3 minutes. So when I plug in 6, the probability has to go up. So it goes up to 0.8647. And if I waited 12 minutes, the chances of me getting a call would significantly increase. So it's about 0.98168. And if you waited long enough, it is certain that we are going to get a call. In other words, the probability will be 1. How long should we wait? Let's say we waited for 2 hours, which would be 120 minutes. And you wonder, well, the average time between incoming calls at a switchboard is 3 minutes, and here we are waiting for 120 minutes, and what is the probability of that happening? It has to be certain. It's bound to happen. So the probability is 1. So beyond a certain point, the probability is 1. 100% chance of it happening. So the decay part here applies to the e raised minus t over 3 term. So that part is going to decay with respect to time, but keep in mind there is a 1 here, and you're taking away a decaying value that is decaying towards 0 from 1, so which is why we end up getting 1 as the limiting value. What do I mean by that? So if limit t approaches infinity, probability of t would be 1 minus limit t approaches infinity, e raised minus t over 3. What happens to an exponential decay as t approaches infinity? The entire term becomes 0, so we have 1 minus 0, and 1 minus 0 is just 1. So, derivative of exponential functions. So, if we have f of x is equal to e raised x, then what is its derivative? Oh no, if we have a linear function which is y equals mx plus b, the derivative of that y prime is just m, which is the slope, and that is constant. Excuse me. In other words, the derivative of a linear function is constant, which would imply the growth of a linear function is constant, and in this case with rate m, and that m is the slope. If something is growing exponentially, the rate at which it's growing must be exponential also. In other words, the growth of an exponential function must be exponential. In other words, the rate at which it grows must also be exponential. So if we have e raised x here, there has to be an exponent over there also when we do find the derivative. So, in short, the derivative of an exponential function is the same exponential function. The derivative of e raised x is e raised x. If we have a constant multiplied before e raised x, then the derivative would still be the constant multiplied by e raised x. If we have a constant added to an exponential when we take the derivative, it would still be e raised x because the derivative of the constant is 0. And if we have e raised a times x, and you take the derivative with respect to x, keep in mind we have a times x, not x by itself, rather a times x. So if we use chain rule, we have e raised ax multiplied by the derivative of ax, which is just a. So still, a is a constant, so we have a multiplied by e raised ax. A special case, the decay function. Suppose a is -1, then e raised -x. We take the derivative, we simply have negative e raised -x. So clearly, if there is growth, then we would have a positive rate of change. And if you look at the derivative here, that is positive rate of change. And if we have a decay function, things are decreasing, so we have a negative rate of change. So growth, decay, and growth means a positive rate of change, decay, negative rate of change. And in short, the derivative of an exponential is exponential, and in general, derivative of e raised ax is simply a multiplied by e raised ax. So if we know these basic properties of derivatives of natural exponents, we can combine this with other rules such as product rule, chain rule, quotient rule, and so forth to find the derivative of complicated functions that involve natural exponents. So here we want to find the derivative of -5e. Now recall, e is a number. It is 2.7182 approximately. So what we have here is f of x is equal to -5 times -2.7182. The entire thing is approximately 13.5 approximately. You could use a calculator. So that means a constant. So f of x is a constant, which implies f prime of x is just 0. A constant doesn't change. In general, derivative of e raised a with respect to x is 0. Because there is no x here. So we have to find the derivative where y is equal to e raised -3 multiplied by x raised 4. Now, if the power were to be just -x, we know the answer would be negative e raised -x. But that is not the case. We actually have -3 x raised 4. So we have to use chain rule. We treat the power of a, or the exponent of a, as x. And what is the derivative of that exponential? It would simply be e raised -3 multiplied by x raised 4. But since it is not x, rather a function of x, we're going to take the derivative of that using chain rule. which would give us negative 3 multiplied by 4x raised 3, the derivative of x raised 4. So y prime would be e raised negative 3 x raised 4 multiplied by negative 12 x cubed. So we can write that as negative 12 x cubed e raised minus 3 x raised 4. This problem is very similar to the previous problem. Instead of x, we actually have a function of x in the power. So we are going to treat the power as x for the time being. So the derivative of e raised x squared plus 7 is e raised x squared plus 7. Then we realize that the power is not just x, rather it is a function of x. So we have to multiply by the derivative of x squared plus 7, which is 2x plus 0. Again, we are using chain rule. So we will end up having 2x times e raised x squared plus 7. So here we have a problem where y is equal to 4x cubed multiplied by e raised minus x. So we have terms in product here. So what I'm going to do is I'm going to write y as 4x cubed e raised minus x. All I have to do is find the derivative of the terms that are inside the square bracket, multiply it by 4 to find the derivative of y. So to find y prime, we must have derivative of x cubed e raised minus x with respect to x. But since there are two functions in product, we have to use product rule. So u is x cubed, v is e raised minus x, du is 3x squared, or u prime, v prime is dv, the derivative of e raised minus x is negative e raised minus x. And we know product rule it's u v prime plus v u prime. So u is x cubed, v prime is negative e raised minus x, v is e raised minus x, u prime is 3x squared. So we have e raised minus x in common, and we have x squared in common. So I could pull x squared and e raised minus x out. So I'll have negative x in the first term plus 3, which is simply x squared e raised minus x multiplied by 3 minus x. Mind you, that is the derivative of whatever that's in there, and we have to find the derivative of y, so we have to multiply it by 4. So y prime is 4 times x squared e raised minus x, 3 minus x. So we have to find the derivative of x squared plus 1 times e raised 4x. We have two functions in product. So u is x squared plus 1 and v is e raised 4x. U prime is 2x and v prime is 4 times e raised 4x. So the derivative of the function is simply u v prime plus v u prime. So we have x squared plus 1 times 4 e raised 4x plus e raised 4x, which is v, multiplied by 2x. We have a 4x in common, so we could pull that out. So, e raised 4x in common. And we also have a 2 in common, so we could pull that out. So we end up having 2 times x squared plus 1 plus x. So we have 2 e raised 4x multiplied by 2x squared plus x plus 2, and that would be the derivative. Here is another function involving natural exponents, but only this time we have natural exponent in the numerator, natural exponent in the denominator. So obviously we've got to use quotient rule. So that is u and that is v, and we know quotient rule states v u prime minus u v prime divided by v squared. U is e raised to x, v is e raised to x plus 1, u prime is e raised to x times 2. Recall derivative of e raised ax is a multiplied by e raised ax. So the derivative of e raised to x is simply 2 multiplied by e raised to x. The same applies here to e raised to x, and derivative of 1 is 0. So f prime of x would be equal to v u prime minus u v prime divided by v squared so f prime of x would be 2 e raised to x multiplied by e raised to x plus 2 e raised to x minus 2 e raised to x multiplied by e raised to x divided by e raised to x plus 1 squared. E raised to x times e raised to x, if we use the properties of exponents, it would become 2 e raised 4x plus 2 e raised to x minus 2 e raised 4x. Divided by e raised to x plus 1 squared. Those two would get cancelled, and we will have f prime of x is 2 e raised to x divided by e raised to x plus 1 squared. And that would be the derivative. So here we have multiple terms, and they all have exponentials, and they all have products. So product there, product there. So what I am going to do is I'm going to find the derivative separately and add them as listed. So y is x squared e raised x minus 2 x e raised x and plus 2 e raised x. So y prime is the derivative of x squared e raised x minus 2 times the derivative of x e raised x plus 2 times the derivative of e raised x is simply e raised x. So that part is easy. Now, the derivative of x squared e raised x with respect to x would mean we have to use the product rule. U here is x squared, v is e raised x, u prime is 2x, v prime is e raised x. Therefore, the derivative of x squared e raised x is u v prime plus v u prime, which would be x squared multiplied by e raised x plus e raised x multiplied by 2x. E raised x is in common and an x is in common. So if we pull that out, we'd end up having x plus 2. Moving on to the derivative of the second term, derivative of x e raised x. So here, u is x, v is e raised x, u prime is 1, v prime is e raised x. So the derivative of x e raised x would simply be u v prime plus v u prime. U here is x, v prime, e raised x, v e raised x, u prime is simply 1. Now we just have to take that derivative and that we found and plug it in here in their respective places. So y prime would equal to the first derivative that we found minus 2 times x e raised x plus e raised x plus the third term is just 2 e raised x. So we would end up having x squared e raised x plus 2x e raised x minus 2x e raised x minus 2 e raised x plus 2 e raised x. Those two would go away, those two would go away. So the first derivative is simply x squared e raised x.